welcome you all. In the first semester course, we have a complex analysis. In this complex analysis, we will discuss some of the basic concept about the complex analysis, how the complex numbers are introduced, and what are the importance, and we will study some complex calculus as well as integration. In this, we will discuss some series and sequence, etc. Here, first we will start with the content of this presentation. We will start with complex numbers, powers and roots, sets in the complex plane, functions of a complex variable, Cauchy-Riemann equations, exponential and logarithmic function, trigonometric and hyperbolic function, inverse trigonometric and hyperbolic function, and complex integration. Let us start with a complex number. What is a complex number? You know that any quadratic equation is in the form of x squared plus 1 is equal to 0. If you solve this, then you get x is equal to plus or minus root 1. In a real number system, we cannot express, we don't have a value for root of minus 1. In this problem, we see that I square is equal to minus 1. We can solve this equation like x square plus 1 is equal to 0. Then that's why root of minus 1 can be represented as I. Note that here electrical engineers use J is equal to root of minus 1, but we will stick with the standard notations used in mathematics and physics. Means we will use only I as a notion. Now we will discuss about the importance of complex analysis. Complex analysis has not only transformed the world of mathematics, but surprisingly, we find many applications in many areas of physics and engineering. For example, we can use complex numbers to describe the behavior of the electromagnetic field. In atomic systems, which are described by quantum mechanics, complex numbers and complex functions play a central role. Now we will start with basic definition how to define a complex number. Any number is of the form z is equal to x plus iy, where x and y are real numbers, and this I is called the imaginary unit is known as complex number. And some, if you z is equal to x plus iy, here we say that x is a real part of a complex number and y is called the imaginary part of complex number. That can be denoted by Re of z is equal to x and Im of z is equal to y. You know there are some properties about the complex numbers. If we identify, suppose if we choose two complex number, let z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2 are said to be equal, means z1 is equal to z2 if the real part of the first complex number is equal to the real part of the other complex number. Similarly, the imaginary parts are also equal, then only we say that the two complex numbers are equal. Suppose if we say that if x plus iy is a complex number is equal to 0, if and only if both real and imaginary parts are equal to 0. In this case here x plus iy is equal to 0 means x must be 0 as well as y is also 0. Now we will discuss about some arithmetic operations of complex numbers. These things you already studied in your UG courses. Suppose if you take two complex numbers z1 and z2, we say that sum of two complex number can also be expressed in terms of complex number. You can see here the adding of two complex number means real part is added to the real part, imaginary part is added to the imaginary part. Means you get z1 plus z2 is equal to x1 plus x2 plus I times y1 plus y2. Means sum of two complex number is again a complex number. Similar way, the difference of two complex number is again a complex number. And also product of two complex number, if you choose z1 and z2 are two complex number, then if you multiply these two, then you get x1 x2 and y1 y2. Here I into I is I square, that become minus, then you get a, the product is real part. Similarly here x y1 x2 plus x1 y2 means here you get the imaginary part, means product of two complex number is again a complex number. Similar way, division of two complex number, if you choose z1 by z2, here you must remember in a complex number system, a complex number cannot be present in the denominator. If the number is present in the denominator, we must rationalize the denominator. Means suppose 1 by x plus iy is there, then we can make the conjugate can also be multiply numerator and denominator, then the denominator become, here suppose a plus ib is there, means a minus ib can be conjugate, the multiply with this you get the real part, means here z1 by z2 you get this one. Again, denominator must be not equal to 0, otherwise it become indeterminate. Next we will discuss about the conjugate. We already told z is equal to x plus iy is a number, then z bar is equal to x minus iy is a conjugate of a complex number. Exactly similar way, the conversely also we can express this. In the conjugate, they are the properties of a conjugate of a complex number. Suppose z1 plus z2 bar can be written as z1 bar plus z2 bar, and z1 minus z2 whole bar is equal to z1 bar minus z2 bar, and z1 into product of z1 z2 whole bar, the conjugate is same as mod z1 bar into z2 bar. Similar way, the division z1 by z2 whole bar, the conjugate can be made as z1 bar divided by z2 bar. There is some important relationship of complex number. A number is multiplied with a conjugate, and the number added with a conjugate. What happens? We can see here. Here z plus z bar means z means x plus I by we have chosen, and z bar is x minus I by, means here if you make this z plus z bar is equal to 2x, means it is a purely real part, real only. Similarly, z into z bar means x plus iy is a z we are expressed, then z this conjugate is x minus iy. It is in the form of a plus ib into a minus ib, means a square minus b square form. Then this become x square minus I square is minus 1, and then it become plus, and y square means this is x square plus y square. Similar way, if you make the number and its conjugate, the difference of two numbers, then x plus iy minus x minus iy means you get 2 times iy, means real part is subtracted, remaining is 2iy. Then using equation 1 and 2, the real part of z can be expressed as z plus z bar divided by 2, and imaginary part of z can be expressed as z minus z bar divided by 2i. Some geometrical interpretation about the complex number. Here, this is the following figure you can observe. figure, this is the figure called a complex plane. We can say that it is a complex plane or organe plane. Because organe introduced this, the pictorial representation of a complex number, that is z is equal to x plus iy. Here if you is vector is denoted by z is equal to x plus iy. Usually, we can also express the complex number in the form of ordered pair, that is x comma y. That can be position vector. It is a position vector that can be expressed in x comma y in the organe plane or complex plane. Now we will discuss about the modulus or absolute values of a complex number. Suppose any number is in the form of z is equal to x plus iy, then its modulus can be expressed as mod z is also a real number. It is root of z into z bar. Means that is x square root of x square plus y square. This is the modulus of a complex number. We will give some examples related to this modulus. If z is equal to 2 minus 3i, then modulus of z means root of here x is equal to 2 and y is equal to minus 3, then root of x square plus y square means it is root 30. Similarly, as in the figure, the sum of the vectors of z1 and z2 vectors is the sum of the vectors of z1 and z2 is a vector z1 plus z2. Then we have mod z1 plus z2 is less than or equal to mod z1 plus mod z2. This is the Cauchy equation, that is a triangular inequality. We also say that it is a triangular equality, and this can also be extends to an finite sum, that is mod of z1 plus z2 etc. zn is less than or equal to individually mod z1 plus mod z2 plus mod zn. Using this, we can also express mod z1 plus z2 is greater than or equal to mod z1 minus mod z2. Here you can see this diagram. Here this is a position vector mod z1, this is mod z2, then this is same as this, means we can make it as z1 plus z2. We can easily observing the triangle inequality in the pictorial form. Now we will discuss about the powers and root. Complex number can also be expressed in terms of polar form. Cartesian form of a complex number can be expressed in z is equal to x plus iy. Then here you can see here in this diagram, z is equal to x plus iy is a Cartesian form. X plus iy, that can also be, I already informed that x comma y. Then if you this is a position vector z, then it is same as r, and here you can see that this is x and this is y. You already know this is x comma y. Then if you take here sine theta, angle sine theta, then this become, what is that, opposite here, cos theta and sine theta. If you express, that is x by r and y by r, then you get, this is the form of r sine theta, this is the form r cos theta. Then you get z is equal to x plus iy, and then z can be expressed as r cos theta plus I sin theta, where r is equal to mod z is the modulus of z and theta is the argument of z, means argument or amplitude of z. Usually the theta in the interval minus pi less than theta less than pi, it is called as principal argument or denoted by arg of z. Here I will give one example related to this conversion from Cartesian to polar form. You know that here this is x is equal to 1 and y is equal to minus root 3. Then sin theta by tan theta is y by x. Then that is minus root 3 by 1. And theta is equal to argument of z. You know that the principal value must be lying between minus pi to pi. Then this is 5 pi by 3. Tan theta is equal to minus of root 3. Then pi minus theta. Then that becomes it is pi by 3 plus 2. Then it is 5 pi by 3. Then because if we express in terms of polar form means this can be expressed as r into cos theta plus I sin theta. We already got the theta value, then we need the modulus value. R is equal to root of 1 square plus root 3 minus root 3 the whole square means it is 3. Then 1 plus 3 root of 1 plus 3 is equal to 2. Then if you substitute you get z is equal to 2 times cos of 5 pi by 3 plus I sin 5 pi by 3 means this is the conversion from Cartesian to polar form. In addition, you know that here minus pi less than theta less than or equal to pi. Therefore, theta is equal to minus pi by 3. Then z can be expressed as 2 into cos of minus pi by 3 plus I sin minus pi by 3 means that become cos of minus theta in the first quadrant. It become, you can see here, cos of minus pi by 3 plus I sin minus pi by 3. Then it is lying here. You can see this is minus pi by 3. This is cos pi pi by 3. Then that definitely lying here. That is 1 minus root 3 minus I. Now we will discuss the polar form with the multiplication and division. Suppose here, if you take two complex number is in the form of polar form, means z1 is equal to r1 into cos theta plus I sin theta, and z2 is equal to r2 into cos theta 2 plus I sin theta 2. Then if you multiply this, you get the multiplication is in this form. You know that r1 r2, if you multiply inside cos theta, again you can see here it is in the form of cos and sine function, and this is also sine and cos theta function. Then it is also a complex form. And also division of two complex number, z1 by z2 is equal to r1 by r2 into, if you simplifying this, you get cos theta 1 cos theta 2 plus sin theta 1 sin theta 2 plus I sin theta 1 cos theta 2 minus cos theta 1 minus sin theta 2. Sin A cos B and cos A sin B form. Means if you're using that, we get the Z1 Z2 is R1 R2 into cos of A plus B form, and that is sin of A plus B form. Then that can also be cos theta 1 plus theta 2 is another theta. Then it is also a complex form. Similarly, the division of two complex number is also in the form of complex, because r1 by r2 is another r3 because it is also a real number, and this is also a function. Thus we can also show that mod z1 z2 is mod z1 into mod z2, and mod of z1 by z2 is equal to mod z1 by mod z2. The properties of modulus is also holds good in the polar form. And argument of z1 z2 is argument of z1 plus argument of z2. Argument of z1 by z2 is argument of z1 minus argument of z2. If you say powers of z means in the polar form, if you express z square is equal to, because z is equal to r into cos theta plus I sin theta, If you're squaring both the inside, then that become r square into cos theta 2 plus I sin theta 2. Similarly, z3 become r cube into cos 3 theta plus I sin 3 theta. Then you get z power n is equal to r power n cos n theta plus I sin n theta. These things you already studied in your PU classes. That is the Demoivre's theorem, the general form. That is when cos theta plus I sin theta to the power of n can be expressed as cos n theta plus I sin n theta if r is equal to 1. And now we will discuss about the roots of a complex number. A number w is the nth root of non-zero number z if w power n is equal to z if we let w is equal to rho times cos phi plus I sin phi. Here instead of theta, here we use phi and another number z is equal to r into cos theta plus I sin theta. Then rho power n cos n phi plus I sin n phi is equal to r into cos theta plus I sin theta, and here rho power n is equal to r and rho is equal to r power 1 by n. Here cos n phi is equal to cos theta, sin n phi is equal to sin theta, then phi can be expressed as theta plus 2k pi by n. K is running from n values, that is 0 to n minus 1. The roots of the corresponding k is equal to 0 is called the principal nth root. Thus, the nth root of the non-zero number z is equal to r into cos theta plus sin theta can be expressed as 2k pi plus theta divided by n into of this. Also we can express cis means cos I into sin theta of theta plus 2k pi divided by n. Now we will discuss about the sets in the complex plane. Sets in the complex plane. Z is equal to x plus iy and z naught is equal to x naught plus iy. Then the distance between z to z naught, that is modulus of z minus z naught, is equal to root of x minus x naught the whole square plus y minus y naught the whole square. You know that here if you make for z minus z naught, because real part is subtracted to real part and imaginary part is subtracted to imaginary. Then the modulus property mod z is equal to root of x square plus y square. Using that property, we can write this. If z satisfies mod z minus z naught is equal to rho, this point lies on the circle of radius rho and centered at the point z naught. This is known as the circle equation, that is mod z minus z naught is equal to rho. Here point z naught is the center and rho is the radius. Now we will give one example related to this. If mod z is equal to 1 is the equation of a unit circle centered at the origin. And another one, mod z minus 1 minus 2i is equal to 5 is the equation of a circle of radius 5 centered at minus, because you know that z minus z naught means here center is 1 plus 2i. If z satisfies mod z minus z naught is less than rho, this point lies within a circle with a radius rho centered at the point z naught. The set is called the neighborhood of z naught or an open disk. A point z naught is the interior point of S if there exists some neighborhood of z naught that lies entirely within S. If every point of S is an interior point, then S is an open set. You can see here we taken the circle means mod z minus z naught is less than means it is inside the points. Mod z minus z naught is less than rho. And this is known as open disk. If it is included means less than or equal to means then we say that it is a closed disk. The graph, if you see here, this is of the form mod z minus z dot is less than r. It is an open disk here. First we can make what is here 1.1. This is 1 and 1.1 comma minus 2i. 2i is this is 2i high positive 2i here. This is a point center. Then we can make a circle with a radius 0.05. 0.05 is the radius. Here, if you see this, it is a circle with centered at this point and radius is equal to 0.05 means it is a open set. One more figure, if you observe that the graph of real part of z is greater than or equal to 1. Means you know that here it is a x is equal to 1. Real part of z means x axis. It is 1. It is show that it is greater than or equal to 1. Means here in this point we can it is not an open disk because it is a closed here. Therefore the real part of z means it is a line, it is greater than or equal to 1. Similarly, here in this illustrate some additional open sets. Here you can say imaginary part of z is less than 0 means this is the lower of plane. If you observe, it is less than 0. Similarly, here this is a real part of z means it is x is equal to 1 and minus 1 is there. It is lies between minus 1 to 1. This is an infinite strip. And these are the interior and exterior of a circle means. Here in this circle, inside the point we say the interior of a unit circle because here mod z is greater than 1 means mod z is less than 1 means that is interior only. It is mod z is greater than 1 means it is outside the point. That is known as exterior of a unit circle. And if you see in this diagram, a circular ring means it is a strip will be there. There are two circles centered at origin and one is radius 1 and another one is 2 is there here means it is the ring circular ring is there here 1 to 2 will be there means these points is known as circular ring or annular ring. If every neighborhood of Z naught contains at least one point that is in a set S and at least one point that is not in S, then Z naught is called the boundary point of S. The boundary of S is the set of all boundary points. If any pair of points Z1 and Z2 in an open set S can be connected by a polygonal line that lies entirely in S is said to be connected, and if you see in this diagram it is a connected. An open connected set is called a domain. This is known as the domain in this diagram. A region is a domain in the complex plane with all some or none of its boundary points. Since an open connected set does not contain any boundary point, it is a region. A region containing all its boundary points is said to be closed. I already mentioned in the previous, if it is the boundary points are included, then we say that it is a closed. You can see here the function. In effect, a function of a real variable maps from one real line to another real line. In the next class, we will discuss about the function and other thing. Thank you.